Hello guys, welcome once more to our YouTube channel. Thank you for hopping in. Today we are looking at StarWest Mock 2023, of course the episode 2. Let's go. Again, we had already looked at episode 1 of this paper, which is 1 to 13. So we are here today. So I mean there are these more episodes to go. So if you have any difficulties with any one of these problems, just write them down. We're coming. So we want to upload all of this series or all of these episodes before Sunday. Alright, so keep checking up the channel for new content every day. All right, let's go. Ooh, guys, just before we go, I have something to show you. Yeah, these guys are super amazing. We do all this work for these guys. They are a huge inspiration for us. They motivate us every day. I mean, like, these guys are just like energy suppliers to us. They smile so great. So this is the Casey family in Boyer. All right, the picture is actually catching out some people, some really nice people here, like Sandrine, Ruda, and yeah, some really amazing humans. So this is our family in Boya, and if you somewhere and you're watching our content and you want to get one of our t-shirts, just leave a message through WhatsApp or on WhatsApp through one of the numbers on the screen. All right, that's my number particularly, so I'll reach out to you immediately. Let's go. Alright, so question 14 says an object of mass 20 grams traveling at the speed of 5 meters per second hits another object of mass 45 kilogram moving 3.5 meters per second is in the same direction, guys. The two objects move together after collision. They move together. What is the loss in the kinetic energy? All right, so let's do basic things. Let's apply the law of conservation of momentum because that's what happens for every collision, right? Because they move in the same direction, so the initial momenta are just added. All right, so the momenta have the same sense. Okay, so you just add them up. They're moving in the same direction. Now they stick together after collision and move with a common velocity. So if they stick together, then you just need to add their masses and they multiply by that common velocity. Okay, so let's make that common velocity the subject. So we get VC there, and then we substitute in our figures. We get our common velocity as 3.96 meters per second. Now, KE loss, of course, is KE initial minus KE final, all right? So we're just going to come over here and find KE initial first. Of course, KE initial, there are two objects here, A and B. So find the initial kinetic energy is half MAUA squared plus half MBUB squared. Okay, so when you plug in the values, 20 grams is 0.02 kilograms. All right, I've not converted here because the final answer is in meters per second. Understand that it does not affect the kilogram, does not affect the final answer. But here the unit of mass affects that because of course the unit of energy is the joule, which of course has the kilogram in there, so you need to convert the unit of the mass to kilograms. Okay, so you get the result as 0.5256 joules. Now you have to go over and calculate the final kinetic energy, but to do that it's very easy. Okay, so half some of their masses, since they stick together, all right, multiply by the common velocity squared. So you plug in the values, and then K final is 0.50596 joules. So get the difference to find the KE loss. You would have K initial minus KE final, which gives us 0.02 joules, and our answer is B. All right, guys, so just pause this video and read the question. All right, so again, but the question is really all about interference and a little bit of diffraction. So can you distinguish between the two very well? If you can, then you have no problem with this question. So I'm just going to talk about interference and diffraction a little bit before we get to the answers. All right, so you notice that these are two sound sources, and then you can put a detector somewhere here along X to Z. All right, so if I put a detect all along here are detectors. Okay, so you can get put to positions where you have minimum, all right, minimum intensity. You get to positions where you have maximum intensities all the way from X to Z. Now those positions of minimum intensity, of course, clearly tells you that the sound waves coming from these two sources meet out of phase, so they cancel out each other, and then a node is formed at that particular point. When you have maximum intensity or maximum amplitude, you get to a point where, of course, the waves coming from these two sources meet in phase, and then of course you have constructive interference, and then you have an antinode being formed there. So if I move all along here, I'm going to get to positions of maximum and minimum, but all those positions are going to have equal intensities because again that is a consequence of interference. All right, so let's just talk about what happens if you instead had a diffraction gradient. So you would shine your waves through. Of course, we're using light waves here. They go through these slits, they get diffracted, and then in this region where they're diffracting, they superpose on each other, and then there's constructive and destructive interference occurring in this particular region. So if I get a screen and then I place it maybe at some distance away from these slits, maybe 1 meter, 1.5, 2 meters, you get interference pattern that is set up. Okay, but now the interference pattern here is not stable. Why? Because the consequence of diffraction. So this diffraction grading indicates that the central bright fringe here would be very bright, but as you go away on either side, it gets darker and darker. You can notice that as you go away from this central bright fringe, the intensity, the brightness of the fringes gets smaller and smaller and smaller and smaller and smaller and smaller, all the way to when you can no longer distinguish between a bright and a dark fringe. Can you see that? Perfect. So that tells you that yes, the intensity of these bright fringes dies out with distance away from the central bright fringe for a diffraction pattern. But for an interference pattern, that it does not happen. So I've just brought out the difference between interference here and diffraction. And remember that this also came in the paper 2 of the Southwest Smog. We're going to talk about it tomorrow, and I'm going to upload that video here so that you guys can check it out. Yeah, so this is a short table that brings out the differences. So maxima have a constant intensity, maxima have a change in intensity for diffraction. All right, so bright fringes are equally bright. Brightness goes on decreasing from the center order. So again, this is about what? This is about their maxima. So again, for interference pattern, they have constant intensity, but for diffraction, they have changing intensity, and the intensity dies out on either side, all right, with the brightness. So for this, since this is a consequence of interference, this is what is happening here is actually interference. Okay, you have these two sound sources, they're producing waves that interfere with each other along this region X to Z. So you don't even have to go and waste your time reading the question. If you understand what it is, then you understand that, all right, so the maxima have a constant intensity, so your answer has to be a maximum intensity at Y and several other positions along X, Y, Z. All right, so because the waves meet in phase here at Y, so you have maximum disturbance, and then all along you have disturbances of equal intensity. All right, let's go. An electron of charge E and mass m moving with speed v perpendicular to a magnetic field of strength B describes a circle of radius r given by, okay, let's, oh, notice that I did not type the answer there. No problems, let's get to work. So if I bring an electron into a uniform magnetic field like this, notice that this is the direction of motion of the electron, and then our field is getting into the page. So notice that they are perpendicular to each other because the electron is moving along the page, the field is getting into the page. So they are perpendicular to each other. That means that, well, the motion of the electron, the charged particle, is circular in this field. Now what happens if the electron gets into this field at an angle theta different from 90 degrees? This is what happens. The motion is no longer circular, the motion now becomes helical. All right, so this is what happens when a charged particle gets into a magnetic field at an angle different from 90. All right, now let's come back here. So because we know that the motion is going to be circular since the electron is moving perpendicularly to the magnetic field, what provides the centripetal force that keeps this electron moving in a circular path? Because we know from mechanics that when objects move in a circular path, it's a centripetal force that keeps them moving in that circular path. So of course that centripetal force is going to be the magnetic force that this external field exerts on that charged particle moving through it. So let's do that. The magnetic force is B curve V. Since an electron, the charge will be small e, all right? So let's just do that and put it at the end. So the centripetal force is mv squared over r from mechanics, so we know that. So of course we know that the magnetic force in this case provides the centripetal force, so Fb equals Fc. So we notice that B curve V equals mv squared over r. So you notice that our r is of course mega subject, you have mv over B curve, and then of course the charge on the electron is E. So we have our answer as r equals mv over Be. So that gives us C as the answer. So 17, what is the coefficient of friction between the 6 kg mass and the horizontal support in figure 4? Given that both masses accelerate at 5 meters per second squared. All right, so this one is easy peasy lemon squeezy. So you just need to demonstrate the forces. The original diagram did not have these forces demonstrated. All right, I did not animate. Okay, I did not animate. All right, so I've demonstrated these forces. The tension is acting in this direction with respect to this 6 kg mass. The tension will be acting upwards with respect to this 10 kg mass, but of course its weight is acting downwards like that. Okay, so you have to indicate that. The friction from this surface will be acting in this direction, and that friction is what? Mu, which is coefficient of friction between the object and the surface, multiplied by the normal reaction, and the normal reaction, because resting on the horizontal surface, will just be the weight, mag. All right, so we multiply those two, they give you the frictional force. So if you indicate all of this, so we can now apply Newton's second law on the system, all right, in the direction of the acceleration. So the examiner indicated this direction. You have to take note that we're applying this direction like this, downwards. So for the 6 kg mass, you would have the forward force minus the backward force. So you have T there minus mu mag equals 6a equals ma. All right, that's Newton's second law. The resultant force on the particle is ma. So for particle B, you are going to notice that, well, the forward force would rather be this weight minus the tension, all right, because we're resolving the direction of this acceleration is downwards. So this weight minus t to be equals to 10a. So we notice that we add these two equations, we are going to have this. We make mu the subject. You'll notice that our mu is that, all right. So just add these two, t disappears, and then you make mu the subject, and then you get mu to be 0.31. So our answer is A. No, the answer is C, guys. Oh Jesus, I did not animate this. This is another error. Please, the answer is C. All right. Okay, guys. So now you have to follow me very carefully through this one. This one is a little bit tricky. So let's go. You have a ray of light moving from air into the core, and then bounces off into the cladding, and then we want the ray of light to be totally internally reflected, so we need it to bounce off the core cladding interface back into the core. Let's do some work. Now I have a question here for you guys. Which of the following interfaces will have the largest critical angle? Glass water, or diamond water, or diamond glass? Now you take the refractive index of diamond to be 2.4, refractive index of water is 1.3, refractive index of glass is 1.5. Tell me down in the comment section below which one has the greatest critical angle. The person who has the right answer, the first person who has the right answer, you will have a shout out in our next video that will be uploaded tomorrow. All right, so let's go. Let's solve the problem. So we complete the diagram here. Okay, so you notice I've completed the diagram here, and then this is our normal here. So our critical angle first off is sine inverse of what? N2 over n1. So the ray of light is moving from n1 from medium 1 into medium 2. The critical angle will just be sine inverse of the refractive index of medium 2 divided by the refractive index of medium 1. Okay, so now we expect that for critical angle to occur, for total internal reflection to occur, guys, there are two measure conditions. The first one is that the angle of incidence in the more optically dense medium has to be greater than the critical angle. Technically, that is the second one. The actual first one is the ray of light has to be moving from an optically more dense medium to an optically less dense medium. For instance, water to air. Then you get to it's possible to get to the internal reflection. Glass to air, it's possible to get to the internal reflection. Glass to water, possible to get to the internal reflection. But if the ray is moving from air to water, never possible. All right. So first, we want the ray to move from a more dense to a less dense medium, optically dense medium. Secondly, we want the ray or the angle of incidence in the more dense medium to be bigger than the critical angle. All right, so this is what we're using the condition 2, that angle of incidence has to be greater than critical angle. So this implies that what? That our theta has to be greater than our critical angle here, which is sine inverse of n2 over n1. Okay, so we go on, and then you use a little bit of geometry here. Notice that, well, this is a right angle triangle here. If I sum up all the angles within this triangle, they give me 180. Okay, so it means that r plus theta has to be 90, because this guy is already 90 here. All right, so that means that our r is basically 90 minus theta. Okay, perfect. So if our r is 90 minus theta, it means that our theta is also what? 90 minus r. So in place of theta here, we're going to put 90 minus r. So 90 minus the r has to be greater than our critical angle, which is all of this. So we can rewrite this, we can solve this inequality. Okay, if 90 minus r is greater than theta c, what does that mean? It means that we can rewrite this as 90 minus theta c is greater than r. Okay, so just reshuffle the position of r and theta c. Now we can also rewrite this as, because our theta c is sine inverse of n2 over n1. All right, so in place of theta c, we are going to put 90 minus sine inverse of n2 over n1 has to be greater than r. Now we're going to go over here and say, all right, if all of this is greater than r, it means that r is less than all of this. That's why we say, okay, r has to be less than all of this. Okay, so you notice that we can use Snell's law now at this air core interface. All right, now if we use Snell's law basically states that, well, the product of the refractive index of medium 1 to the sine of the angle of incidence has to be equal to the product of refractive index of medium 2 with the sine of angle of refraction. If we compute that, you notice that our refractive index of air is basically just 1. I here would basically be sine inverse of n1 sine r. Okay, so we're making r the subject, so we take sine inverse on both sides. So you notice that we have sine inverse of n1 sine r. Now, but guys, notice that our r here remember, arrow is this range. Arrow lies in this range for total internal reflection to occur. So we're going to collect this range for arrow and then substitute in the equation for I, so that we convert this equation to an inequation getting a set of conditions or a range of values for I, such that total internal reflection occurs. So r is less than all of this. Put that inside this expression in place of r. You'll notice that you have 90 minus, right? So it's less than that. So you place this in, so our I is going to be less than all of that, okay? So that means that we have a certain maximum value that if you go beyond that value, you're never going to get total internal reflection for this incident angle. So that maximum angle, you can only get total internal reflection for incidents in this light at smaller angles and never bigger than. So that angle is called the cut-off angle, okay? So the maximum value for the angle of incidence on the fiber for which total internal reflection occurs is called the cutoff angle, okay? It's usually less than 25 degrees. If you plug in the values for actual refractive index of cladding and that of the core for a typical optical fiber, you notice that this angle in this particular question gives you something about 24 degrees, which is ideal for what we are talking about. All right, okay guys, so that was a question. Clearly you notice that there was no answer there, so our answer is known. All right, so we move on. Following thermodynamics second law, for any process guys, that may occur in an isolated system, which of the following is applied? Okay, we're just going to talk about entropy a little bit, but a change in entropy is actually the change in amount of work done on a particular system divided by the temperature. Sometimes this work done is expressed as a change in the heat content of the system. That's why you see me writing dq. The S there, of course, if we want to sum up all the various change in the heat content, all right, of a particular system, if there are tiny little changes, so we can sum up all those little heat changes at a particular temperature interval from a certain initial condition of the system to a certain final condition. If we sum up all those changes, we are going to get the total change in the entropy. So we simply just look for this integral, and then we get the total change in the entropy of that particular system, okay? So now the problem, however, is that in a reversible process, of course, it's a process where the initial and final states of the system are identical, all right? So I equals to F, so these initial and final conditions are equal. That tells you that what? If I integrate this thing and I put upper limit minus lower limit, it basically gives me 0 because upper limit is equal to lower limit, all right? So there's no change in entropy for a reversible process. That entropy stays constant, all right? Now, the problem, however, is that every reaction that occurs in real life is not reversible. It's not a reversible process, all right? So every real life reaction or process is an irreversible process, okay? So that means that it's just like you have real gases and ideal gases in, thermodynamics. Real gases are what you have in real life. Ideal gases are just hypothetical scenarios. You don't really have ideal gases in real life, all right? You just get a real gas and then you put it under some conditions, all right? And then you get it very close to ideal gas conditions, all right? Yeah, that's what you do. All right, so for irreversible processes, all processes in nature, all right, you notice that, well, if I get this data, the change in entropy, the integral from I to F of this particular expression, I and F are different. So when I do this integral, it's of course different from 0. When I get the absolute value, notice that it's greater than 0. That tells me that, well, the entropy can actually either decrease for any system or stays the same, but it would never decrease. And that is the second law of thermodynamics in terms of entropy. That's what I've stated here. The entropy of a system can never decrease. So next time you are asked in the exam to state the second law of thermodynamics, you can just basically say that, well, the entropy of a system can never decrease. It's that easy. All right, so our answer here is D. For a single electron, the electric field strength 0.1 nanometer away from the charge is, okay guys, let's look at this. This one is easy peasy lemon squeezy. So electric field strength is K cure over R squared, okay? So K is 9.0 times 10 to the 9. Cure is a charge on an electron, because we're using an electron here. It's 1.6 times 10 to the negative 19. R, the distance away, is 0.1 nanometers, okay? You square that, so you have our answer as 1.4 times 10 to the 11. Sorry, I did not put the 11 here, guys. All right, so the answer is actually to the 11, sorry. So our answer there is A. If the fundamental frequency of a transverse vibration of a wire fixed at both ends is 300 hertz, guys, fundamental frequency fixed at both ends. Okay, now if the tension in the wire is doubled, the new fundamental frequency is, guys, what is fundamental frequency? Now watch what is happening here. You see this string fixed at both ends, vibrates at its fundamental frequency, the least possible frequency of vibration of this particular string, that is fundamental frequency. Now notice that from this node to the next node, what is that distance? It's lambda on 2. All right, so the length of this string L is basically equals to lambda on 2. So what is lambda? Lambda is equals to 2L. So 2 times the length gives me the wavelength. Now let's do some maths here. The wave speed for transverse waves is basically the square root of tension divided by the mass per unit length of that material, of that string. Okay, so since speed is equals to lambda f, okay, so f would be speed over lambda, so that's why you see 1 over lambda in front of here, from this place. Okay, that's our f. Now because we're talking about fundamental frequency, we'll be talking about the wavelength at the fundamental frequency, which is basically what, 2L. That's what we've just talked about here. So this wavelength, we'll talk about 2L here. All right, so f naught is 1 over 2L square root of t over mu. So you notice that our new fundamental frequency now, when we double this tension to 2t, will now be what? The length has not changed. We have just only doubled the tension in this string. All right, the length stays the same, the mass per unit length stays the same. So you now have f nu would now basically be what? Just this 2 that is changing. So we're going to factor out the root 2. If we send out that root 2, we're going to have 1 over 2L square root of t over mu. All of these things at this square bracket is the same exact thing that we had for the fundamental frequency. So what does that mean? It means that when you double the tension in this wire, the new frequency basically increases by root 2. That's what that means. So you have root 2 multiplied by our original fundamental frequency, that gives us 424 Hertz. So our answer is C. Which of the following is true for an object describing circular motion? Guys, watch this object. Watch, just watch. Watch what's happening. Look at the length of this arrow. It's not changing. This is the velocity vector. But now the direction is constantly changing. Now it's pointing west. Now it's pointing south. Now it's pointing east. Now it's pointing north. North, east, west, west. You see that the direction is constantly changing, right? The same thing with this acceleration vector. It's pointing now west, now southwest. So the directions are constantly changing, but their magnitudes are the same. All right, because the length of this line indicates the magnitude of that vector. The direction indicates the direction of the vector, because, well, a vector quantity has two components to it: its magnitude and its direction. All right, so you notice that because the acceleration and the velocity vectors are the same in magnitude, but their directions are constantly changing. That means that they're actually changing, because those vector quantities are a combination or a composition of their magnitudes and their direction. So again, the answer here clearly is just B. All right, yeah. There's more to say here, but I just don't want to waste time. All right, because again, you can talk about non-uniform circular motion, where this the length of these arrows will be changing. Okay, because there will be a component of acceleration along this line, which is what you call the centripetal component of the acceleration, or the centripetal acceleration in short. And then you will also have a component of acceleration along this vector line, like this, the velocity vector line. And that component is what you call in further maths the transverse component of the acceleration. So you have the radial and transverse component of the acceleration. This transverse component will be changing the magnitude of this velocity. Let's really not get there. All right, guys. So yes, so that's what happens in this particular simple case that you see in physics, and the answer is just B. Guys, it's enclosed. All right, just pause the video and read the question. All right, guys, so you notice that our work done here is basically just PdV. This one is very easy. So P is that I'll take the change in volume, final volume minus initial volume. All right, so multiply that, you have 400 joules. Our answer is D. Which of the following statements about an n-type semiconductor is not correct? Not correct, guys. So all are correct except one. Okay, it has a Hall voltage polarity that is reverse of that for a p-type semiconductor. Correct. All right, if you are n-type, you have majority charges to be negative electrons, and your polarity would be opposite to the polarity of the guy who has majority charge carriers to be positive, which are basically holes. We'll talk about this in a moment. It is electrically neutral. Correct. All right, but if you increase the temperature sufficiently high enough, you would start exciting electrons from the valence band to the conduction band, and so the conductivity of semiconductor material increases with the increase in temperature. B says majority charge carriers are electrons for an n-type. Correct. So obviously A is wrong. It is an intrinsic semiconductor. Wrong. N-type means that the majority charge carriers are negative, which means that, or electrons, which means that you get a naturally existing semiconductor material like silicon, and then you dope it with a pentavalent atom, all right, so that there are excess electrons, and those excess electrons, they basically form what is known as the majority charge carriers, all right. So if I want to form holes as the majority charge carriers, then I have to dope a semiconductor material like silicon, all right, purely existing semiconductor material like silicon. I dope it with a trivalent atom like boron or aluminum, all right. So if I dope it with that, then I form an extrinsic semiconductor, which is a p-type, all right, because majority charge carriers now becomes holes instead of electrons. Okay guys, so let's talk about this D part a little bit. Hawes voltage, let's talk about Hawes voltage a bit. Hawes voltage is actually set up when you get a current carrying material like this and place it perpendicularly to an existential external magnetic field. So you have the electric current flowing like this from left to right in this material. You place the material and then such that this field is perpendicular to the direction of flow of this current. Guys, you're going to set up a PD along the sides of the material, and this PD is known as the Hawes voltage. Let's look at how that comes about. First, let's talk about this current that goes through the material. Okay, so I equals never, this is what you did in lower state, right? So V drift velocity is I over NEA. So of course we can get to a point where these charges have drifted to one side, the electrons have drifted to one side, until, so when they drift to one side, they create an induced positive N, because all the electrons are moving towards this side. So this N becomes positively charged, all right, by, of course, induction. So when the electrons move this way, they induce positive charges on the other side. Okay, so now the charges stop growing on this side if the effect on the magnetic force on each one of these charges counteracts or directly equals the effect of the electric force on each one of the charges. Okay, so at that point you say Fe equals to Fb. That's where you stop. That's where the Hawes voltage now becomes steady. All right, so now we're going to get Fe, of course, is electric field intensity multiplied by the electronic charge, and then of course magnetic force on an electron is BeV. We've seen this previously. So we make those things a subject. Our electric field intensity is basically what? The PD between these plates divided by the distance. All right, what's the distance? The distance will just be the width, because this is the length, this is the width, and this is the thickness. So the width here would basically be the distance that is separating these two polarities. So we'll get that intensity as what? VH over the width. Now we're going to make VH the subject. So you notice that our VH is all of this expression here. So this means that, well, we can come down here in place of area. What is our area? This cross-sectional area here. The area is width times its thickness. All right, because the electric current goes through this particular surface. You notice that this is the only surface that is important for the electric current, because it is perpendicular to the direction of electric current. Okay, so you notice that, well, we can put those things and then we compute. You notice that our Hawes voltage will be Bi over NET. So our answer is A. All right, so 25, which of the following is true about electromagnetic waves? Guys, I'm just going to make you watch what happens in an electromagnetic wave. Watch that. Watch that. So let's say that the electric field is oscillating in the y direction, all right, this blue field, and then the B field, the magnetic field, is oscillating the z direction. Can you see this z plane that I've indicated here? So this is it oscillating in, out, in, out, in, out. So you notice that these fields are oscillating perpendicular to one another, because of course the y and the z planes are perpendicular to one another. You know that from math. Now the direction of propagation, the wave, the disturbance is propagated in which direction? Along the x direction. We can see that the waves are moving, all the motion is moving what? From left to right along this x direction. So because the y, z, and the x planes are mutually perpendicular planes, you know this from math. So it tells you that the direction of propagation of the wave is perpendicular to the direction of each one of the vibrating particles that produce the wave. And the vibrating particles in this sense are really not particles but vibrating fields. Okay, so that's really how electromagnetic waves are produced. They are transverse in nature because they move perpendicular to the direction of the vibrating fields. Okay, so clearly you can have made some statements here. The answer is already C, but I've made some statements here for you. The first one is the electric field component determines a plane of polarization. So this electric field component, like you see this blue guy, this is the guy that determines the plane of polarization of an electromagnetic wave. I've just said that out there, so hope you've taken out your book to jot that down. Point 2, phase difference means an oscillating component leads or lags another in time or in space along a plane of oscillation. I'm going to explain. In electromagnetic waves, the B and E fields have different planes of oscillation which are mutually perpendicular, hence why B is wrong. So notice that B is talking about phase difference. They're out of phase. Listen, it does not make any sense when you talk about two things being out of phase if they're not first of all vibrating in the same plane. You talk about current and voltage when you're studying AC circuits being out of phase or in phase because they are oscillating in the same plane, and then maybe one can lead one can lag one. All right, maybe when one is climaxing, the other one is at the minimum. So yes, I'm leading you, but we are oscillating in the same plane. These guys are oscillating in two different planes. One is oscillating the Y plane, one is oscillating the Z plane. You don't talk about phase difference in this case, okay? You don't. That's why B is off. Then EM waves are transverse in nature, meaning the direction of travel is perpendicular to the direction of vibration of particles producing them. We've already talked about this, right? Which is why D is wrong. So our answer is C. Okay. Our last problem, guys, is a problem of mechanics. I'm just going to let you read it and I'm going to do the analysis here. So the first part of the motion is when you start from rest and then you attain maximum velocity. Now when you attain maximum velocity, you travel that maximum velocity all the way to the finish line. All right, so when you get to the finish line, all right, you've covered 100 meters. Now let's do some math here. The first equation of motion, v squared equals u squared plus 2as. Once we use this first part first. All right, so of course let's make s the subject. We get that, and our u is 0, v is 8. All right, because you attain maximum velocity at this particular point. You put all those things into place. Our s1 is 12.8 meters. This is the distance you cover here. Now we can go over here and calculate the time for which you cover that distance. Of course, we can just say v equals u plus a t1. So our t1 would be, make t1 the subject, so you put v and a there, so you have 8 over 2.5. so the time there is 3.2 seconds. Now if I go over here, I can actually calculate the distance that I'm supposed to cover for that is left for me to cover, because I simply need to take a total distance 100 minus the distance s1, so that gives us 87.2. so that means that our s2 would be, we can apply this, okay, this equation of motion, but again notice that this part like that would be 0. Why? Because the particle is not accelerating when it's covering s2. Remember that it has already hit maximum velocity. All right, so when you hit maximum velocity acceleration is 0 at maximum velocity. So s2 equals u t2. So what does that mean? T2 is s2 over u. So what is our u here? Our u is the velocity which you travel this direction, the initial velocity, and that is already v max, okay, 8 meters per second. So you put that in, you get our t2 to be 10.9 seconds. So our total time will be t1 plus t2, which means that our total time is 3.2 plus that, so 14.1 seconds. So our answer is A. Alright guys, so we have come to the end of our series. Thank you so much for watching. Please subscribe, share our content out there to your classmates, your friends, or your social media, your groups. Massive thanks to those supporting us. We are super grateful. We are honored. Everybody here is honored. You can see this is Bradford here, one of the key people that are helping us with this typing process. And then there's Jane. This is Jane out here. This is her amongst the staff here. And then this is myself, and then there's Luis, of course, our chief project officer. So many amazing people at KC. We're doing all we can so that we can help you in your preparation process. Massive thanks to those sharing and commenting. Please like, comment, leave as many comments as you can. Thank you so much. Stay curious always.